Lecture is going to be a quick, short crash course on Group 17 from AS Inorganic Chemistry. So these over here are your Group 17 elements: fluorine, chlorine, bromine, iodine, and acetine. First thing that you need to remember about these Group 17 elements is that in the neutral states, they always exist as diatomic molecules. So, for example, you will never see fluorine as a single atom. A fluorine atom is going to bond with another fluorine atom to form an F2 molecule. Same happens with chlorine. It's always in the form of a Cl2 molecule, a Br2 molecule, and so on. We'll also quickly go over the dot and cross diagrams. All group 17 elements have 7 valence electrons. So as you can look at the fluorine atom over here, there are 7 electrons in its valence shell, and it needs 1 electron. So it's going to try and attract 1 electron from the other fluorine atom. The other fluorine atom also has 1, 2, 3, 4, 5, 6, and 7 electrons. So it needs 1 electron. So it's going to try and attract an electron from the other fluorine atom. What would eventually happen is that the 2 fluorine atoms would start sharing electrons. So they would both be pulling each other's electrons, and eventually what would happen is something like this would happen, that they would start sharing the 2 electrons in the middle, and that would end up forming the fluorine molecule that is shown over here. Another thing that you must remember about group 17 is that as you go down the group, the melting and boiling points increase and volatility decreases. For example, if you look at fluorine over here, which is a gas, chlorine is also a gas, but when you move to bromine, bromine is a liquid and at room temperature, and iodine is a solid and acetine is a solid as well. Now, to explain the trend in melting points and boiling points, what you must first know is that these are simple molecular structures, which means that there's a tiny F2 molecule, there's another tiny F2 molecule, another tiny F2 molecule, small F2 molecule, and these molecules, they have very weak intermolecular forces between them. These weak intermolecular forces, they are called van der Waals forces, and the way these van der Waals forces are formed is because if you look at the molecule over here, it's a non-polar molecule, which means that the electronegativity difference between the 2 fluorines is exactly the same, which is why this molecule would be non-polar. The electrons are going to be evenly distributed around the molecule. But during random collisions, these molecules bumping into each other, these electrons which were previously in an isolated environment, they must be equally distributed. There should be no partial positive or partial negative charge on this molecule. But during collisions, what happens, since these are gases, they're not attracting each other very strongly. What would happen is that the electron distribution is going to get disturbed. The electrons, during bumping into other molecules, the electrons might get knocked to either side. So for a very temporary instant, this side could be partial negative, this side could be partial positive. The electrons could be more concentrated on this fluorine rather than on this fluorine. So this would be your temporary dipole, and this temporary dipole is going to create an induced dipole on this molecule because the partial positive fluorine is going to attract electrons in this fluorine molecule towards itself, and that will disturb the electron density of this fluorine molecule. The electrons would be closer to this fluorine, they would be more concentrated on this fluorine because the electrons would be attracted to the positive charge over here. And this side will get a partial positive charge. So they are temporary dipoles formed, and they are induced dipoles formed because of the temporary dipoles that are forming on one molecule. Same temporary dipole induced dipoles would also be formed on this molecule. So once the molecule becomes polar, the slight positive side of one molecule will attract the slight negative side of the other molecule. The slight negative side of this molecule will attract the slight positive side of this molecule. So there would be some force of attraction. Very weak force of attraction, but there would be an intermolecular force which would be called van der Waals forces, or in other words, it's called temporary dipole induced dipoles. These van der Waals forces depend on the number of electrons. It depends on the size of the molecule. So as you go down the group, so if you move down the group, let's take iodine. Iodine has a lot stronger intermolecular forces, a lot stronger van der Waals forces, because the van der Waals forces are going to be greater in iodine. So here I've drawn the structure of iodine. The intermolecular forces in iodine are a lot stronger. And the reason being that iodine is a much bigger molecule. It has more electrons. Now, bigger molecules, more electrons would lead to stronger temporary dipole induced dipole, because if you have more electrons getting knocked around on one side or the other side would lead to a much stronger partial negative, partial positive, or a temporary dipole would be formed that would be much stronger compared to fluorine. Fluorine only had 9 electrons each. So 9 electrons on either fluorine, that makes 18 electrons. So if 18 electrons get knocked around, the partial positive, partial negative charges are not going to be very strong. An iodine molecule has a total of over 100 electrons in it. So if 100 electrons get knocked on either side, then the partial negative, partial positive charges are going to be a lot stronger, and the force of attraction or intermolecular forces between iodine molecules, one partial positive side of one iodine molecule attracting the partial negative side of the other iodine molecule, the attraction is going to be a lot stronger, and that is why iodine is in solid form whereas fluorine is in gaseous form. So a quick summary, all these molecules have simple molecular structures, and they have van der Waals forces, and these van der Waals forces depend on the size of the molecule. More electrons, stronger tempty dipole-induced dipoles. So fluorine, because it's a smaller molecule, its attraction between molecules is going to be weaker. Iodine, being a bigger molecule, has stronger tempty dipoles-induced dipoles, and its attraction with other iodine molecules is going to be a lot stronger. Hence, volatility decreases down the group. Thing you need to remember about group 17 is their colors. The colors of group 17 are that fluorine is very pale yellow. It's almost colorless. It's a gas, but it's a very, very pale yellow gas. Chlorine is greenish yellow in color, so it's a greenish yellow gas. Bromine, on the other hand, is orange brown. Sometimes it's also called red brown. It's going to be an orange brown liquid. Iodine, in its solid state, is a black solid, but if you heat it, it's going to form a purple vapor. Iodine can also dissolve in water, and if it dissolves in water, it forms a yellow solution. If the concentration of iodine in solution is in aqueous state is very high, then it forms a brown solution. So it's a yellow-brown solution. Acetine, although it's not in your syllabus, but one trend that you're going to notice is that as you go down the group, the colors become darker. So since acetine is not in your syllabus, but following the trend, acetine is going to be a black solid. You started off with pale yellow, then greenish yellow, then it became darker, orange-brown, then black solid. And acetine is also going to be a black solid. As you go down the group, colors become darker and darker. Let's also discuss quickly the electronic configuration of all group 17 elements. As you can see, fluorine is the outer shell. Focus on the outer shell. Fluorine has a 2s2, a completely filled S subshell, and a P subshell that has 5 electrons in it. Underlined are all the outer subshells, and you're going to notice that they are all exactly the same. It's always S2 and P5, S2 and P5. The shell number is changing. You have more and more shells, but the outer shell always has an S subshell that is full and a P subshell that has 5 electrons in it. They all have 7 valence electrons, and the outer shell always has an S2 and a P5. The thing that's important is about oxidation states. That's based on the electronic configuration. Fluorine cannot expand its octet, and its oxidation state is always -1, whereas chlorine, bromine, and iodine, they can expand their octets, and they have multiple oxidation states. So let me explain this in a slightly more detail. So here is fluorine's electronic configuration again, and you would notice that the outer shell has a 2s subshell and a 2p subshell, and there is no other subshell. These are the only spaces available where electrons can be accommodated. So there are no further subshells available in the second shell. This is the second shell that I've drawn over here. This is the simpler version, 7 electrons, and there is no other room available. There's only room available for 1 electron. So only space available for 1 electron, and that electron is going to be either shared or gained. It can either form an ionic compound or a covalent compound. But what it can do is it can only accommodate just 1 electron from another element, whether it's sharing that electron or whether it's gaining that electron. Now, if you look at a chlorine atom and its electronic configuration, this is the electronic configuration that's written. And what you would notice is that chlorine's outer electrons are in the third shell. The third shell is much bigger compared to fluorine's second shell. The third shell has more subshells, there are more spaces available. So although chlorine has the same electronic configuration for the outer shell, there's an S subshell and a P subshell with 5 electrons in it, but there's a completely empty D subshell. So chlorine can accommodate 1 electron, or it can accommodate at least 11 electrons. There are lots of spaces available over here. So empty subshells are available in the third shell, so more electrons can be accommodated. So there are lots of empty space available. So for chlorine, it can gain 1 electron, but it can also gain more than 1 electron, or it can accommodate more than 1 electron because of this completely empty there are 5 3D orbitals in one subshell. So there's 5 3D orbitals that are available, which can also accommodate electrons. I'm going to show you a polyatomic ion where chlorine is making more than 1 bond. It's accommodated more electrons. Instead of just accommodating 1 electron or gaining 1 electron, it's accommodating a lot more electrons. So you have these oxygen atoms that are trying to form double bonds with chlorine. So they're going to share their 2 electrons and 4 electrons for oxygen are going to be left over. This oxygen would also do exactly the same. It's going to share 2 electrons, and 4 of its electrons would be left over, whereas one of the oxygens would end up forming a dative bond where the oxygen atom is not contributing any electrons. So its 6 electrons, valence electrons for oxygen, are not used, but it actually ends up gaining 2 electrons from chlorine, so it ends up forming a dative bond. Now this is a molecule of ClO3, and the reason why it has a negative charge is because 1 electron, chlorine's octets or orbitals are not paired, so it gains 1 electron from outside, which gives it a -1 charge. So this is an example of a molecule which is ClO3 -1. In this molecule, chlorine ends up gaining or bonding, it ends up forming 5 bonds. A double bond over here, a double bond over here, a single bond over here. So it ends up forming 5 bonds, and over here the oxidation state of chlorine is +5. So the reason why chlorine can form multiple bonds or can accommodate more electrons from more atoms is because it has empty outer subshells in its outer shell. And the same applies to bromine and iodine as well, because their electronic configuration doesn't really end at 3s and 3p. There are lots of empty subshells. As you go down the group, you have bigger shells. Bigger shells have more subshells, more spaces where electrons can be accommodated. So they can have, they can form 1 bond, they can gain 1 electron, or they can gain a lot more than 1 electron as well. So chlorine, bromine, and iodine have multiple oxidation states. As you can see over here, I've listed some of the common oxidation states. So fluorine is always -1, as I've told you. It always is gaining 1 electron or forming just 1 bond because it's not capable of octet expansion. Chlorine can be NaCl. It could be Cl -1, ClO -1, or ClO3 -1. So it can form all these polyatomic ions, ClO -1, ClO2 -1, ClO3 -1, ClO4 -1, where it can have multiple oxidation states. And the same pretty much applies to iodine and bromine as well. So iodine and iodates and bromates, bromine, etc., the same compounds, the same oxidation states could be formed. Just replace Cl with Br, or it could be iodine. So all these compounds, all these polyatomic ions can also be formed with the bromine or iodine. Now, one very common reaction that you must remember, which is based on these common oxidation states for chlorine, bromine, and iodine, is that you must remember. So the reaction of chlorine with cold NaOH must be remembered, and you must know the balanced equation as well. So remember chlorine, or it could be bromine or iodine as well. Chlorine reacts with cold NaOH to produce NaCl. Sodium chlorate 1 is produced and water molecule is produced. But if you react chlorine with hot NaOH or hot concentrated NaOH, then the reaction produces NaCl again, but this time sodium chlorate 5, a higher oxidation state for chlorine, a compound containing high oxidation state of chlorine is formed, and water molecule. So they're similar equations. The only difference is in the first reaction with cold NaOH, sodium chlorate 1 is produced, and with hot NaOH, sodium chlorate 5 is produced. And also remember, the similar reaction would occur with bromine or with iodine as well. Let's now quickly discuss bond strengths, especially of the halogen-halogen bond. For example, there's an F2 molecule, a Cl2 molecule, Br2 molecule, and I2 molecule, and I've plotted the bond enthalpies or bond strength of these molecules, and you would notice that the general trend is that the bond energy or the bond strength is decreasing down the group. But fluorine over here is not following the trend, and it has a weaker bond compared to all the others. Now I've drawn the diatomic molecules. This is a fluorine molecule, F2. This one over here is a Cl2 molecule. Its bonding is also shown. And this one over here is a bromine molecule. Now what usually happens is that all these electrons, they're sharing these 2 electrons. All of them are sharing 2 electrons each. So these 2 electrons are being shared in each molecule. But what's going to happen is, and usually the trend is that as you go down the group, the size of the atom becomes bigger and you have more and more shells. So because of the more shells, the nucleus, the attraction of the nucleus, these 17 protons, they would not be attracting these shared electrons very, very strongly compared to fluorine, where the nucleus is very close to the shared electrons and there are lesser shells and lesser shielding. So as you go down the group, you're going to have weaker bonds. The size of atom increases. You have more shielding, more distance, and there's less orbital overlap. So the nucleus of the 2 atoms, they would not be attracting these electrons very strongly. In the case of bromine, this is going to be even worse. The protons are even more shielded by these electrons. So these protons and these protons over here, they would not be very strongly attracted to the electrons, shared electrons over here because of the greater distance. and because of the because of these lots of electrons over here that are shielding the nucleus. So this nucleus would be even these electrons would be even less attracted to the nuclear. So orbital overlap is going to decrease, and the bonds are going to become weaker, which is shown over here as well. So you can see on this graph that iodine has a very weak bond, bromine has a stronger bond compared to iodine, and chlorine has a stronger bond compared to. So the smaller the atom, the stronger would be the bond. So smaller atoms are going to have stronger bonds. So smaller the atom, stronger would be the bond. There's going to be more orbital overlap. But the problem over here is that if you look at the trend is followed by the three elements at the bottom, but not by fluorine over here. So fluorine is not following the trend exactly. Fluorine actually has a weaker bond compared to all the others. So what is the reason why fluorine has a weaker bond? Now, one of the reasons why fluorine has a weaker bond is because atoms of group 7 have a lot of lone pairs. So you can look over here, there are lots of lone pairs of electrons, or electrons that are not involved in bonding. So it has 3 lone pairs. Each fluorine atom have 3 lone pairs. Now, fluorine is such a small atom that what eventually happens is that if they get together to bond and they start sharing electrons, these lone pairs, they're going to exert a force of repulsion on each other. They would strongly repel each other because of these extra electrons in its outer orbital. These electrons are going to repel each other. They're going to start repelling each other very, very strongly because they're going to be very close in this molecule over here. And this repulsion, it is because of this repulsion that the bond in fluorine would actually weaken. There's going to be more repulsion rather than the attraction. The nuclei, instead of getting attracted to the shared electrons, they would instead be repelled. The two atoms would be strongly repelling each other. The lone pair of one atom would be strongly repelling the lone pairs of the other atom, and this would make it very easy for fluorine, or it would make it very easy for the bond to break. So fluorine hence has a much lesser bond strength or bond energy, and the reason is it has a weaker bond because of the lone pair repulsion. And this factor is not that prominent in the bigger molecules, because in the bigger molecules the atoms are much further away from each other. So these lone pairs and these lone pairs, they're further away from each other, so they're not going to repel each other very strongly. In the case of bromine, the lone pairs over here are going to be very far away from the lone pairs of this atom over here because of the bigger size. So they're not going to repel each other very strongly. But that happens, that is a problem with fluorine over here because it is such a small molecule. Let's now discuss the bond strength of hydrogen halides, which are basically HF, HCl, HBr, and HI. And as you can see over here, the trend is perfectly followed. Bigger molecules are going to have weaker bonds. No element is there's no element that is not following the trend. So the trend is perfectly followed. The reason is that in the previous case of fluorine, one of the atom has lone pairs, the other atom has no lone pair. So the lone pair repulsion factor is not present in any of the molecules. So the only factor that is present is that bigger atoms are going to form weaker bonds because they're more shielded, they are more distance, and there's going to be less orbital overlap. So bromine over here is not going to be attracting the shared electrons very strongly because of the large number of inner shells that I have not drawn over here, but they are present. Inner shells are going to shield the nucleus, and the nucleus and the shared electrons are not going to attract each other very strongly. So in the case of fluorine, the attraction is going to be very strong because fluorine is a small atom. The nucleus is going to be very exposed. It's not going to be shielded, and it's going to attract the shared electrons very, very strongly. So HF has the strongest bond, whereas HI has the weakest bond. Now we're going to discuss the melting and boiling points of HX, and this graph over here is for the boiling points of hydrogen halides. X is the halogen. So you can see over here that HF has a very high boiling point. HCl, HBr, and HI have lesser boiling points compared to HF, which means that HF has very strong intermolecular forces compared to all the others. So I've drawn two HF molecules over here. Now fluorine is one of the most electronegative elements in the periodic table, which means that fluorine and hydrogen is going to have a very polar bond. All the electrons would be very close to fluorine, so the dipole created is going to be very, very strong. So fluorine is going to have a very strong partial negative charge, and the partial negative charge would be even stronger because of the high electron density of these lone pairs. It's a small atom. The lone pairs are very strongly concentrated in a very small region, so there's a very high electron density. So the attraction between these lone pairs and the neighboring positive hydrogen is going to be very, very strong. So because of these hydrogen bonds, the melting point and the boiling points of HF are going to be very high compared to the others. Now the other molecules, as you move down the group, the electronegativity decreases. Cl is less electronegative, bromine is even less electronegative, iodine is even less electronegative. So the bonds become less and less polar. So the partial positive and partial negative charges are going to become weaker and weaker as you go down the group. So weaker dipoles would be formed. Permanent dipoles would be formed. So two HCl molecules are going to attract each other, but they're not going to attract each other as strongly as two HF molecules. HI molecules would attract each other, but they're not going to attract each other as strongly as HBr molecules. So because of the weaker attraction, the boiling points of the three molecules, they must decrease. But as you can see in the trend, you would notice that the boiling point is actually increasing. And the reason why it's increasing is that although the permanent dipoles that are formed are becoming weaker, but the overall size of the molecule is actually becoming bigger. So the bottom molecule is going to have more electrons. So if it has more electrons, although the bottom molecule is going to have weaker dipoles, but it has more electrons, which means that there would be more temporary dipole-induced dipoles. There would be stronger van der Waals forces. So two things happen down the group. The dipoles become weaker, but at the same time, van der Waals, they become stronger. So the overall effect is that the van der Waals become more dominant as you move down the group, which is why HI molecule would attract another HI molecule more strongly compared to two HCl molecules. Although HCl has a stronger dipole compared to an HI molecule, but because of the greater van der Waals forces, because of more electrons in HI, the temporary dipole-induced dipoles in HI molecules are going to be more. So, which is why the trend is going upwards if you compare the three. And again, I'm summarizing that HF is going to be different from the others because HF has hydrogen bonds. The electron densities of these lone pairs is going to be very concentrated. So the lone pairs are going to attract the positive, very, very polar positive hydrogen. It's going to attract, there's going to be a very, very strong attraction, and the intermolecular force is going to be hydrogen bonding. The next thing that we're going to discuss is that electronegativity decreases down group 17. Electronegativity is the tendency for an atom to gain electrons. Now, group 17 is probably one of the most electronegative elements in the periodic table because they're always gaining electrons. So, electronegativity of these elements is going to decrease down the group. Fluorine is going to be Fluorine is one of the most electronegative elements in the entire periodic table. And as you go down the group, it's decreasing. The tendency to gain electrons is decreasing, mainly because there's more shielding, there are more shells, so it's more difficult for the nucleus to attract electrons, and the atoms become bigger in size. If they become bigger in size, then those atoms, it's harder for them to attract. It's harder for the nucleus to attract electrons. All these group 17 halogens, they would like to gain electrons, and they like to form negative ions. So fluorine would try to gain 2 electrons to form 2F-1 ions. Similarly, iodine would also like to do the same. But which one is the most electronegative element? It's fluorine. Fluorine has the greatest tendency to gain electrons. As you move down the group, they become weaker oxidizing agents because all these elements, they're getting reduced. So elements that get reduced are because they're gaining electrons. Elements that get reduced are always acting as oxidizing agents because they're trying to pull electrons from other elements and trying to oxidize them. So they are all trying to gain electrons. They're getting reduced, so they're good oxidizing agents. But as you go down the group, they become weaker oxidizing agents because fluorine is the most it's a small atom, it's the most electronegative element, so it has the highest tendency to gain electrons. Iodine being the bigger element, bigger atom, it's not going to gain electrons very easily. The nucleus would be too shielded, so it's not going to attract electrons very strongly. So it's not going to be a very good oxidizing agent. So down the group, as you move down the group, they become weaker and weaker oxidizing agents. So remember, the elements down the group, they become weaker oxidizing agents. Vice versa, when we talk about halides, the opposite, the negative ions, they would lose electrons to form the element back again. So F-1 loses electrons to form F2. I-1 would lose electrons to form I2. Now down the group, they're going to become stronger reducing agents because down the group, as you move down the group, it would become easier to lose electrons because the elements, so for example, I-1, this ion over here is going to be more shielded. It's going to have a bigger ionic radius, so it would be easy for it to lose electrons. Smaller ions would have more difficulty losing electrons because the nucleus is not going to be that shielded, so the nucleus would be attracting electrons very strongly. So as you go down the group, the tendency to lose electrons actually becomes easier. It becomes easier to lose electrons. So I-1 is it's a very powerful reducing agent. It likes to lose it. It gets oxidized very, very easily. F-1 is a very bad reducing agent because it doesn't like to lose electrons. Now, using the previous idea, we're now going to discuss the reaction of halides with sulfuric acid. Now, the first reaction is of NaCl, which has Cl-1 ion. I'm going to react it with sulfuric acid, and you're going to get sodium hydrogen sulfate and HCl gas would be produced. This HCl gas is going to form misty white fumes of So misty white fumes of HCl gas would be observed in this reaction. What happens in this reaction is that if you have an NaCl and you drop sulfuric acid on top of NaCl, what's going to happen is that the ions are going to mix up. And when these ions mix up, then these H+1 ions from sulfuric acid and these Cl-1 ions from NaCl, they would react with each other and they would end up forming HCl gas. And that HCl gas is going to escape the container in the form of misty white fumes. So that HCl gas is going to escape and leaving behind what is left behind, NaHNSO4 would be left behind. So the NaHSO4 crystal is going to be formed in solid state, whereas HCl gas or HCl vapor is going to escape. So there's a displacement reaction. So a displacement reaction happens, and sulfuric acid in this case is acting as an acid because it's acting as a proton donor. In this reaction, sulfuric acid donated its H+1 ions to Cl-1. So it's acting as a proton donor, it's acting as an acid. Now, when it comes to the reaction of NaBr with sulfuric acid, pretty much the same reaction happens and you get exactly the same reaction, but in this case, you're getting HBr gas. But as soon as that HBr is formed, the problem is that Br-1 is a pretty good reducing agent. That we just studied the trend in reducing agents. Down the group, reducing agents become more powerful. So Br-1 is a very good reducing agent. So HBr as a reducing agent would start reacting with sulfuric acid, which now is not behaving as an acid. But H2SO4 is also a weak oxidizing agent. So next to a reducing agent, sulfuric acid starts behaving as an oxidizing agent. And sulfuric acid gets reduced to sulfur dioxide, whereas Br-1 over here gets oxidized to bromine. As you can see over here, Br-1 getting oxidized to bromine and H2SO4 getting reduced to sulfur dioxide. So a redox reaction starts happening. And the reason why a redox reaction starts to happen instead of the displacement, initially the displacement happens, but the reason why a redox reaction happens is that Br-1 is a pretty good reducing agent. It likes to lose electrons. One observation that you're going to see in this reaction is that a reddish brown bromine gas would be formed because when bromine or bromide ion get oxidized, bromine is formed. Now moving to NaI with sulfuric acid, so the initial reaction is the same, you get a displacement reaction, but remember that I-1 or I-1 is the most powerful reducing agent in the whole of group 17. What this powerful reducing agent would do is that it could undergo several reactions with sulfuric acid, where sulfuric acid would be acting as an oxidizing agent and I-1 would be acting as a reducing agent. So you have these several reactions. This is acting as an oxidizing agent, this is acting as a reducing agent. Similarly, in this last reaction as well, this is acting as a reducing agent. Sulfuric acid is acting as an oxidizing agent. So different reactions could happen, different redox reactions could happen to different degrees. So for the first one, HI could react with sulfuric acid, a redox reaction could occur, sulfur would be reduced and iodine would be oxidized and iodine would be formed. In the second reaction, again, sulfur is reduced, this time into elemental sulfur, which is going to be a yellow solid. And again, iodine gas is going to be formed, iodide ions would be oxidized. And in the third reaction, similar reaction, sulfur is even further reduced to H2S. And again, iodide ions are oxidized to iodine. So you could have three different redox reactions, starting with the first displacement reaction. But very quickly, redox reactions would occur because I-1 is a powerful reducing agent. Now, several observations can be made here. Sulfur is seen as a yellow solid, hydrogen sulfide is a strong smell of bad eggs, and iodine is produced as a violet purple vapor. So you can write three different observations for this particular reaction. I'm going to quickly go back and give you a brief overview. We started off with NaCl. Cl-1 was a pretty bad reducing agent. It wasn't a very good reducing agent. So with sulfuric acid, only a displacement reaction happened. And when we moved down the group, Br-1 became a better reducing agent. So with sulfuric acid, a displacement reaction happened, but immediately the Br-1 started a redox reaction with sulfuric acid because it was a good reducing agent and started getting oxidized to bromine. And the third reaction was with NaI. I-1 was one of the most powerful reducing agents in group 17. So it started off with a displacement reaction, but very soon it changed. It converted into a redox reaction where I-1 got oxidized with sulfuric acid, and sulfuric acid in each case got reduced. And three different types of reaction were possible. So all those reactions would occur to different degrees, and you would get three different types of observations depending on the reaction that's happening. Now, one more thing that you must know is that if you look at the above reactions that we just discussed, the formation of hydrogen halide it's not always the case in all the reactions. For example, in this reaction, all the hydrogen halide it got oxidized. All of it got oxidized, and you did not get HI at the end of the reaction. Instead, all of it got converted into iodine. Same was pretty much true for HBr as well. The reaction of NaBr with H2SO4 did not result in the formation of HBr because most of the HBr then got oxidized to bromine. It was only in this first reaction, that NaCl with H2SO4 were you getting hydrogen halide. HCl was being formed, because in all the other reactions it eventually got reduced. It eventually got oxidized into other products. Now, to get HCl, HBr or HI, so if you want to form only the hydrogen halide, you have to prevent the redox reaction from happening. So you have to stop the redox reaction from happening. And one way to stop the reaction from happening is to use H3PO4 instead of sulfuric acid. If you use H3PO4, the thing with H3PO4 is that it's not a good oxidizing agent. It's not an oxidizing agent at all. Whereas we were using sulfuric acid previously, and sulfuric acid did act as an oxidizing agent. So H3PO4 is not an oxidizing agent. So no redox reaction would happen, because for a redox reaction, you need a reducing agent and you also need an oxidizing agent. So if H3PO4 is a pretty bad oxidizing agent, then no redox reaction would be happening. So NaCl with H3PO4, only displacement would happen and HCl gas would be formed, and no further reaction would happen. Same is the case with NaBr. It's going to produce HBr. NaI, it's going to produce HI. The reactions are pretty similar, except for the fact that afterwards there's not going to be any redox reaction because H2SO4 is missing. For example, in the previous reaction, it was not only HI that was formed that was acting as a reducing agent, but you also needed an oxidizing agent. Sulfuric acid was a pretty good oxidizing agent, which is why you were getting a redox reaction. But with phosphoric acid, if phosphoric acid is in its place, then nothing would happen. No reaction would happen because phosphoric acid is not an oxidizing agent. Now going to discuss the reactivity of halogens and why it decreases down the group. As you can see in the table, all halogens, they react with hydrogen to produce hydrogen halide. And what you would notice is that the first reaction with fluorine, the reaction is very explosive, even in dark conditions, whereas the reaction of hydrogen and chlorine is explosive only in sunlight, but not in dark. Hydrogen then reacts with bromine as well, but it reacts very, very slowly, and you need heating for that. And as you move even further down in the group, the reaction with iodine and hydrogen, it never reaches completion. It ends up in an equilibrium reaction, and it requires heating. The reason it reaches an equilibrium is because as soon as HI is formed, HI decomposes back again to form H2 and I2 again, because the HI bond is very weak. So starting with a very vigorous reaction, you end up with a very slow reaction which does not even reach completion and ends up in an equilibrium. Finally, we're going to discuss the test for halide ions. Remember, all halides have a very typical test, and the test is with silver nitrate. So what happens in the test is that the silver ions in aqueous state, the silver ions generally come from silver nitrate. They react with the halides if they are present in the solution. The halide and the silver ions, they get together to form a compound of either AgCl, AgBr or AgI, which is going to be a solid precipitate. And the precipitate is going to have different colors. So if it's Cl-1, the precipitate is going to have white color. If it's Br-1, the precipitate is going to be cream colored. And if it's I-1, it's going to be pale yellow or yellow colored. And another part of the test is that what you try to do then is that you try to dissolve the precipitate in ammonia. Now, Cl-1 or AgCl precipitate dissolves in ammonia, in dilute ammonia as well as in concentrated ammonia. Whereas Br-1 and I-1, they don't dissolve in dilute ammonia. But if you use concentrated ammonia, then AgCl and AgBr, their precipitate dissolve. But AgI, the last one, it still remains insoluble. So at the end of the day, what happens is that AgI, the precipitate of AgI is insoluble no matter if it's dilute ammonia that's being used or concentrated ammonia that's being used. The precipitate of Cl-1 is soluble in both, whether it's dilute ammonia or concentrated ammonia. The only difference is that the Br-1 precipitate does not dissolve in dilute ammonia, but it needs concentrated ammonia to dissolve. Now we're going to discuss the uses of halogens and the compounds. The first one is that chlorine is used to kill bacteria, especially in drinking water. What happens is that you add chlorine to water, it disproportionates and produces HCl and HClO. Now this chloric 1 acid that is being produced, it decomposes slowly in water to form HCl and produces oxygen atoms. These oxygen atoms are then, they're very reactive, and these oxygen atoms or oxygen radicals are then used to kill bacteria. Halogens also form part of organic compounds which are known as halogenoalkanes, which are frequently used. They have different uses. They form polymers, etc. One polymer is PVC. You also have PTFE. And these polymers are used as plastics in everyday life. PVC is normally your industrial pipes, etc. Your plastic pipes and tiles, etc. are made from PVC. PTFE is the Teflon, that is the non-stick in cooking utensils. Then a lot of CFCs are also produced, which are harmful for the environment, but these are also produced using halogens. And these CFCs are inert and volatile substances that are used as aerosols and refrigerants. Another CFC, a brominated CFC, is also used in fire extinguishers. So CFCs that contain bromine are used as fire extinguishers.